calculate these ones, and then get the evolution of these solutions. Right? This is straightforward. And also, again, is that because the Hamiltonian is a quadratic form, so the path integral is only contributed by stationary paths. Namely, it is given by the classical dynamics. So let's see what kind of classical dynamics you have. You determine, integrate out, or trace over the mode 2 and get equation motion to determine the density matrix of the mode 1 by those two stationary equations. As you see, that those equation motion is very complicated. It is far beyond what we originally understand. But if there is no coupling between two modes, then those coefficients, as you see explicitly, those functions are dependent on the couplings. So if there is no couplings, system go away, system go away, system go away, and the system, because of coupling, is also go away. That's the original equation for the single photonic modes or harmonic oscillators. But if it couples to another mode, you have additional terms. The additional term, this is purely induced by the coupling between two modes. But the right side of the equation actually is induced by the initial state of the mode 2. Alpha 2 means the initial state is in the equivalent state. And then there is explicit dependent gamma. Gamma is a squeeze parameter. So we define the second mode in the coherent square state. So you have those terms. And the more amazing is that you see everything comes from this Hamiltonian initial state, but those terms broke the causality. Why? The tau is the intermediate term between starting point and the end point is the path integral. So tau is less than t and larger than t0. But the contribution to such equation motion takes the contribution from switches. From t0 to t means t is larger than tau, right? So the stationary path of mode 1 is not only controlled by the past historical evolution, but also by the future dynamics. That's what called the block of the causality. Probably this is the first equation motion that you can see in the literature, how explicitly block the causality, but derived from the deterministic quantum mechanics. Okay. Then how we solve this equation, right? If it blocks the causality, computationally it's hard to solve it, right? But fortunately, based on the experience we are working on the open quantum system in the last 20 years, we can easily get the solution. So let's go back to think about, before I talk about the solution, let's talk about the physics. So usually, the physical picture of two modes quantum dynamics. You have the one photon come here, one photon come here, through the splittings, then you get the two outer set, right? That's the test-put experiment that people usually use to explain about the probability interpretation or about the many-order interpretations. Because if we do the measurement, based on the probability interpretation, the state will jump to here. You don't see this one. But based on the many-order interpretation, you can have both. You measure this one, so you go to one order, then another order you never see. Right? But those are the fairly ideal case. Actually, it is not the real physical world. It is just our imaginations. Because when you prepare the single photon state, we already heard lots of technologies that are developed, for example, in the morning's talk. People have well control about the single photon state. But the single photon state is very difficult to define in theoretical world. Because single photon means you have the simple frequency. Then that is wave function in the time domain. You have from minus infinity to the plus infinity. You cannot write a pulse, right? So ideally, theoretically, there is no way to write the wave function for the single photon. What means a single photon means it is a well-packed. So it is a well-packed, such kind of like the coherent state with a very small parameter alpha 1. That's corresponding to the single photon state, because the high photon state has a very small coefficient that can be ignored. But still, it is a vacuum state plus one photon state, a superposition state. And alpha is a small parameter. It means that very hard to propagate. Okay? Then another state we have said is a squeeze coherent state. So that here, the dot means the shape of the well-packed. Then we squeeze the shape of the well-packed, and then go through the beam splittings. And quantum mechanically, actually, you really don't know what happened inside. For the equation motion, actually, from system, we see that there are many processes go back. Then you need to put them together to get the solutions. And then, if it is a square state, you have other contributions. Other contribution will make the causality break. Okay? So, if S is not equal to 0, you have those terms. If it is 0, then those terms will go away. So the equation recovers the causality. So it is the squeezing parameter eventually induce the backwards of those propagators, and then generate entanglement. So we see how the entanglement appeared. Actually, at this point, we don't see the entanglement, right? So let's solve the problem, okay? Now, the solution. The equation motion that blocks the causality actually has a simple solution. The solution contains two terms. One is the past effect, one is the future effect. They are combined together, okay? So all the solution analytically solved because the problem is too simple. Okay, I will go a little bit fast, okay? So the solution, obviously, how the causality is broken. But the source function, time-dependent function, actually is nothing but the very general non-equilibrium function in the many-body system. And here, you find that they perfectly agree with each other. You can use non-equilibrium functions applied to the two-body system and get the same solutions, okay? So those are the mixing, the two modes combined together, you get the normal modes. Okay, now, finally, we need to solve the state. The state analytically can solve it. It gives you all those kind of a problem, solutions. And this is a mixing state. Mixing state means that the original state is an entanglement state. But if, okay, so the mixing state, you have the probability interpretations. Why you have a probability interpretation? Why you have the entanglement? Because the dynamics block the causalities. Block the causality. If we set the square parameter equal to 0, then you will find that all those terms will go away. Namely, here, only the term for n equal to 0 contributed. Then it became a pure state. It's a separate of a pure state. Okay. So this is a very simple system that can be solved analytically. But if you use a path integral, you can really see the detailed dynamic evolution, what happened, and how the entanglement emergence, and how the probability description appeared. So we don't need the Goldberg's interpretations. Quantum mechanics itself includes such kind of properties inside. Dept, we overlooked it, okay, in the past. Okay, so now we understand the problem. Why entanglement emerges only in quantum region, not in classical mechanics. And this is the solution, give you how it broke down. Those are the amplitude in here, delta. So delta not equal to 0 means this became a mixing state. Otherwise, it's a pure state. Okay. So we answer those questions. Why entanglement emerges only in the quantum regime, not in the classical world? Because of the causality break. Why